Hey everyone, in this video we're going to talk about confidence intervals. So typically when we look at a sample, we then try to talk about the population based on that sample. Now it's very difficult to ever know anything about a true population of people because there's too many data points to collect. Or sometimes the statistical question is just something that can't be answered. We just don't know it. So what we can do is, in the past, we've created a point estimate. And so we've used X bar and said, you know what? We are assuming that this X bar represents mu, which is the population mean. But it's actually better to have an interval estimate, because then we know that, and we've seen recently that we can grab one sample, even if it's a large sample of 50 objects, we can grab a sample of 50, let's say, out of a population and get a mean that seems significantly lower than the actual mean, but still have that be within the normal range of variability. And so what we want to do here is we want to create an interval that we hope will capture the parameter that we're looking for, usually the population mean. And so how we do this, so we're trying to capture a parameter. So we're creating an interval that we hope captures this parameter. Now the interval is either going to capture it or it's not, but it's hard for us to know whether that's true because we don't know the population parameter. So what we do is we set a level of confidence. And so this alpha that's here is the same alpha that we've been dealing with. That is our significance level. And here, 1 minus the significance level is going to be my confidence of interval. So if we're looking for, if we were going to do a hypothesis test at a 0.05 significance, that would be the same thing as a 95% confidence interval. And what this confidence interval states, this level of confidence states, is that if we were to repeat this process 100 times, let's say, that we grab 50 randomly selected objects from a population and find the mean of it and create a confidence interval from that mean and standard deviation, if we did this process 100 times, we should expect that we actually captured the population mean 95 out of those 100 times. So let's go about how do we find the confidence interval, okay? Now this process is only going to be for samples where n is large, n is greater than or equal to 30. So here we have a sample of 100 stat students who took a test, and the class average on the exam was a 75 with a standard deviation of 12. So we're going to find a 95% confidence interval for the true average of this test for everyone who's ever taken it. We have one sample, and that sample gave us a mean of 75 and a standard deviation of 12. But we want to know, what is the mean for anyone who's ever taken this test? So the 95% confidence interval, the way that we calculate this is we think about our normal distribution. Now what we know is that the sample that was taken here is 100 students. So this is a large sample. And so we know that the sampling distribution is going to be normally distributed. And if I know that it's normally distributed, I can use all the properties that we've been talking about in my normal distribution. What I know is that 75 is going to be in the middle of this thing. And that's going to be the center of my confidence interval. Now, what I'm trying to find is what value is going to be here and up here, so that 95% of the values in this sampling distribution fall between those values. Okay? Now my standard deviation here is not going to be 12. It's going to be, if I were going to set up 3 standard deviations away from the mean, I'm not using 12 as that standard deviation. I'm going to use 12 divided by the square root of 100. I'm going to use 1.2 for that value because this is a sampling distribution, not a single exam score from one student. This is a mean from a group of 100 students. So what we're trying to do is we're trying to find this lower bound here. Let's do that in red. And this upper bound such that 95% of our values fall between it. Now the way that I calculate this, I already know how to do this. This is an inverse normal problem. And so the inverse normal always starts with all the area that's below a value. So this area right here, if this is 95% in the middle, that means that 5% is split between the two tails here. So this is a 0.025 area right here. And up here would be another 0.025 area. So to find this value first, what we're going to do is we're going to use our norm inverse function. So I'm going to write down what my proportion is. I'm going to write down what my mean is, and I'm going to write down what my standard error is. Because remember, this is a sampling distribution. Oops, that's too big. Okay, so my proportion here for the first value, this value here, okay, that's the one I'm finding first. My proportion is 0.025. And again, I got the 0.025 because I know there's 5% left in the tails here, and I cut that in half. So 5% divided by 2 is 2.5%, and 2.5% written as a decimal is 0.025. The mean is 75, and the standard error is going to be 12 divided by the square root of 100, the size of my sample. So now I use my norm inverse function to create the lower portion of my interval, my confidence interval. So what I'm going to do is I'm going to put parentheses just in this box, and I'm actually going to align that to be to the right. And then in this cell, I'm going to use my norm dot inverse function to find this red value that has the arrow pointing on it, at it, and that's going to be this value, comma, this value, comma, this value, and comma. So that gives me 72.648, and so I know that this value was actually 72.65. All right. Now I need to find the upper bound. Remember, the norm inverse function always finds the area below the point that I'm looking for. So if this is 0.025 plus another 0.95, that means there's 0.975 below this second value on the graph. And so my proportion is going to change for that to be 0.975. The mean's going to be the same, standard error is going to be the same. Now I'm just going to do a fancy formatting trick in Excel. You don't have to do this. This is just stuff that I like to do for fun. So I'm going to put in quotes a comma so that I actually have the interval. So there should be a comma in your interval, lower bound, comma, upper bound, and the parentheses mean I'm not including the endpoints. So this is interval notation. And norm dot inverse, and we're going to find this, comma, this, comma, this. And that comes out to be 77.352. So 77.35. I'm going to go ahead and end the parentheses. And there's my confidence interval. And if you don't like all the parentheses that are here, I think you can set the number of decimal places to be a certain amount. I don't know if I'm going to be able to find it. Oh, decrease decimal places. I don't think you can do it because of the way that I've formatted this. All right, so there's my confidence interval. We have our lower bound, which is 72.65, and our upper bound, which is 77.35. And what we could say is that, because it does ask for us to interpret this. So what we would say is that 95% of the time that we go through this process, we will capture the true mean of the population. And so let me just get some of this drawing out of the way. So again, if we were to repeat this process many, many times, we would capture the actual mean of our distribution 95% of the time. So that means 5% of the time we create a confidence interval and the mean, the actual population mean, just isn't in it. And even within that 5%, it's not always 5%. It could be a little bit less, a little bit more. The more times we do this, the closer we're going to get to a 5% error rate and a 95% accuracy rate. But by creating the interval, we have made it so that we now have a range of values where we think that the mean of the population is located instead of giving just a single value of 75. So now let's go through the same process with a 99% confidence interval. So again, I need to find the proportion, the mean, and the standard error. The proportion now, we're taking 95. So looking at this same picture, now 99% is in the middle, which means there's only 1% being split between the two tails. And so that means for the lower bound, 1% split in half is half of a percent. So that's 0.005. The mean is still 75, and the error is, standard error should still be the 12 divided by the square root of 100, which is 1.2. So now, and the upper bound would be the 99% plus the 0.005, the 0.5% that was below, which gives us a 0.995 for the upper end. And what I can do is I can, because of the way that I've formatted this, I can just take these cells and I can copy them and paste them down below, and I should get my new confidence interval already calculated. See, these values are a little bit different because they're drawing from these cells down at the bottom instead of the cells up top. And so I just copied them over and can use them. So what do we notice about this interval? Again, let's interpret this. 99% of the time we go through this process, we will have captured the true population mean between 71.9 and 78.1. So which interval is wider, and why do we think this is? Well, it looks like the second interval is wider. Why do you think this is? Well, think about it. If I'm more confident that I have captured the mean, if I do this process 100 times, I'm only not going to capture the mean once, don't I need to make my interval a little bit wider so that I'm more confident that I've captured it? Nothing else about this problem has changed. The population mean is the population mean, and I captured it or I didn't. So the larger the interval that I have, the more likely it is that I captured the interval. And so I could say with 100% confidence that I've captured the mean if I said that the range of values was between 0 and 100. But that doesn't give us a very narrow interval to work with. The second interval is wider because we need a wider interval to have more confidence that we have captured the population mean. All right, so that is our introduction to confidence intervals. We're going to come back in the next video and do an example that reviews hypothesis testing for large samples, and we'll actually use a confidence interval to show how finding a confidence interval and doing a hypothesis test are actually one and the same. All right, I'll see you in the next video.